we have to be able to pick one of its constructors to satisfy. Here we don't really have a choice. We have to pick type var. So if we were to generate an expression given a context and a type such that this holds, we need to generate an evar. So we know that at the end, we're going to need to generate a variable of some sort. Then we have to go back and start satisfying the preconditions. So we have to be able to generate an x such that x is bound to t in gamma. And to do that, we have exactly such a generator from earlier on in the talk. We wrote a small function, get gen typed ID from context, that gets a context and a type, and returns an identifier that you can use. Yes, this is the one that was doing the filtering and the one-offs. And it's interesting to note that this is the bind of the G option monad. I haven't used any options anywhere in the entire thing, except to say that the generator is an optional generator. So you're able to avoid all the manual plumbing of the maybes. Let's do a slightly bigger generator. So we keep the evar case, and we add all the base cases of the typing relation. So we add the numbers, we add and the Boolean constants. Again, in order to satisfy has type, we have to pick one of the constructors to satisfy. And the generator for evar can be exactly the same that we saw before. So we can just gen type evar that we saw in the previous slide. And to generate numbers or Boolean constants, it's also fairly straightforward. If the input type is a nat, we can just generate an arbitrary number and return it. If the input type is a Boolean, we just pick one of the two constants. And here I mean pick in the sense of we're defining a list of possible generators we can use in order to satisfy has type. But how will we pick from that list? Well, we saw a few options yesterday. We saw one-of and frequency. But here I'm going to introduce a different one, backtrack. Its typing signature is almost identical to the one of frequency. So it takes a list of natural numbers and generators and returns a generator. With the difference being that the generators here are necessarily optional. So generators for options of some type. Just like frequency, it's going to pick one of these generators to satisfy and produce things with based on the natural numbers. So you can skew the distribution as much as you want. However, if we were to use frequency to pick from the list that I showed yesterday, and we picked the first option, for example, there is a possibility that gen-typed evar can fail if, for example, the context is empty. Using frequency, that would mean that the entire generator would end up returning empty. Backtrack, instead, will, if it encounters a situation where the generator produced a nothing, a none, then it will go ahead and backtrack and pick a different option, allowing you to complete the derivation. So if you're producing a none from the first option, it's going to go ahead and fall through and pick a different one, for example, an arbitrary natural number. As a side note on distributions, here the weights are arbitrarily chosen almost. It's just, the only thing I'm trying to ensure is that constants have equal probabilities. So if you want to have true and false be, you want to have true and false be half as possible as generating a natural number to achieve that. Okay. We saw how we can handle base cases. How can we handle the recursive cases? So all I have here is again the variable rule, and I have the addition rule as well, which just says that the two sub-expressions have to be of the same type as the whole. If you have a typing derivation involving plus, and you want to produce if you want to produce an arithmetic expression like that, it's very close to generating a binary tree. because you have, for every node, you have 2 subtrees that you need to generate. And as we saw yesterday, we need the size bound. We need an extra fuel argument to enforce termination and to control the distribution. So we're going to do just that. Let me bring the bottom up a bit more. We're going to do just that. When the size is 0, we're only going to choose from the base cases, so we're only going to generate variables. But when the size is not 0, we have a choice. Again, we can choose to generate one of the base cases, but we can also choose possibly to generate a plus. When can we do that? Well, we can only do that in this case when the type is appropriate, because we can generate a plus when we want to generate a Boolean expression. But in order to generate a natural number, we could generate a plus where the 2 subtrees have been generated recursively with the same function with size 1 smaller. And this is exactly the way we could go about all the other typing rules that we have. And in fact, this is the full generator. It is slightly larger and slightly annoying to write, but it's extremely straightforward. So you have the base cases, which we've already seen and I don't show in the slide. You have the plus rule, which we saw in the previous one. Minus and multiplication is literally exactly the same. You just use a different constructor in the beginning. Yep.
From an engineering / maintenance standpoint, how do you add constructors to your language with this approach? Or is not how, but have you found any tricks in order to maintain? Because you'd have to add the new generator for the new constructor.
I agree, and that's why at the very end of this talk I'm going to show how everything I'm doing now is basically not necessary to do, and you can do it with automation. But you need to be able to do that in order to be able to fix those generators when something goes wrong, or be able to tweak their distribution when something goes wrong. So this lecture is mostly about showing you what the automation does under the hood, because this is pretty close to what the generator that you could get for free is. And best practices to debug such generators when you start writing them by hand. Because in a fairly large development, there will be a time where you will need to dive in and do something by hand. And while a push-button automation approach is perfect for the beginning, you start a new development, you derive everything, get some maybe not perfectly efficient generators for free in the beginning. As you scale up your development, you will need to skew the distribution by hand. You will need to focus on a specific part of your expression language. For example, you want to generate more variables because you know your substitution has something funky in it, or something like that. And then you will need to dive a bit under the hood. And that's exactly what this is about.
Can you show the bottom of the...
Yep.
For a while?
Yep. So we defined the base in the previous slide, and this defines a generator for the recursive ones. Yeah. And all this does is, for size 0, we backtrack on the base cases. For size not 0, we backtrack on the base cases plus the recursive ones. Yeah, so backtrack is the combinator that I showed earlier. Just picks one of them and keeps going until it succeeds. Okay, any more questions? Good. Now, writing generators is writing a generator like that is slightly complex. It's more tedious than hard. And when you do something tedious, at least I am very prone to making mistakes. Fortunately, we can use QuickCheck to find those mistakes. What do I mean by that? Well, we want to be able to, we said that our generator only generates expressions that are typed in a given context. Well, we can test that. We can literally just generate an arbitrary context and an arbitrary type, then generate an expression of the type that we want, and if generate an expression option, and if the option is none, we fail. Why do we do that? Well, the whole point of writing this generator by hand was to avoid filtering type terms, was to avoid generating terms that are not well typed. So our generator should be able to always generate a successful expression. And then, if we have generated an expression, we are assuming that that expression has the correct type. And that kind of sanity check for the generators is really useful to have. So if you get nothing else from this lecture, this is something I want you to get. If you are going to write a generator yourself, make sure you add some sanity checks to it. Make sure it does what you want it to do by testing it. Because testing it is actually free. You just wrote the thing that it generates. Just make sure that it does what you thought it did. And in fact, there is an exercise later on in this chapter that requires you to write such a generator and a shrinker. I would very, very highly recommend using this approach and testing that it does what you think it does. Okay, let's keep going. Eventually we'll finish up and test the property that we want. Values and states. In IMP, since variables ranged over only natural numbers, we didn't need a specific type for value. They were just nats. Here, since identifiers range over both, we have to have a type for values that includes both natural numbers and booleans. And again, we can just show that. We can easily capture what it means for a value to have a specific type. Natural values have type tnat, Boolean values have type tbool. We can also decide when a type has a specific value, when a value has a specific type. And we can generate a typed value fairly straightforwardly. So if we want to generate a natural number, we just generate an arbitrary number and wrap it in vnat. If we want to generate a Boolean, we generate an arbitrary Boolean and wrap it in vbool. So nothing fancy going on here. But we are going to need to put values in a map. So just like we put types in a typing map to have context, states in TIMP are just maps from identifiers to values. And we're going to introduce a notion of a well-typed state when the state is in complete agreement with a context. So a well-typed empty state, a state is well-typed for an empty context if it's an empty state. And the state is well-typed for the inductive case if the identifiers that are in the front of both the context and the state are exactly the same, and the value has the appropriate type as defined by the context. And of course, the tails are well-typed as well. We can easily decide this relation as well, and the details are highlighted. But this is the property that we want for states, for well-typed states. Here, we could have done something slightly different. We could have just said that the binding of every element is the correct one according to the typing context or something like that. This has the caveat of not dealing with duplicates in the state, not dealing with shadowed bindings and anything like that. So it's slightly easier to generate. But there's nothing that we couldn't do with a different approach in principle. Okay. Let's write a generator for well-typed states. Given a context, all we need to do is generate a typed value based on the type in the context and wrap it together. That produces a list of generators for values. However, we want to go from a list of generators for values to a generator for list of values. The ones that are Haskell inclined will just tell you this is just the sequence operator from the monad. And Quickseek provides that operator. And I'm not sure if xlib does, and we could just replace it with that. But we have sequence gen. It's just sequence for the instantiated for the gen monad. You give it a list of generator options, and it sequences them together to produce a generator for a list of the things that you want. So far, yeah. Evaluation. Here's an evaluation relation. I'm not going to go into too much detail through it. This is literally just saying that if you give me a state and an expression, I will get you the value that it gets out, and fail if you do something stupid like try to add 2 booleans. But I've also done something stupid myself and introduced a very silly bug. I couldn't actually introduce a bug that makes any sense other than a copy-paste bug. So here, let's assume that we were trying to write the conjunction and they just copy-pasted the addition thing and left a natural number evaluation somewhere there. And then because I couldn't actually finish it, I just negate the first one. Something. It's a very silly bug, but it's interesting to see what we can do to find it and how to write the checkers for it. Also in the volume, there is a different chapter, a new chapter, Quick-Check tool, that talks about mutation testing. So we have a way of introducing these bugs in comments so you don't have to pollute your basic development with silly bugs and comments like this is a bug, this is a bug. But your main development will be the correct version. It would be this one. And there's a small notation that says this is a mutant or introducing any mutants you want and testing them. I don't think we'll cover any of that in this summer school. But you should take a look at it and give us your feedback if you have any. OK. Soundness. Finally, we have a property that we want to test. The standard mantra in programming languages is well-typed programs cannot go wrong, right? So that is a conditional property that says that if a program is well-typed, it cannot go wrong. And that's exactly what our soundness will be. If a state is well-typed and an expression is well-typed for the same context, then evaluating the expression in the state cannot return none. It cannot fail with a type error. And to test this property, we can actually write a checker. This checker is fairly similar to the one we had for testing our generators. It does the same thing in producing a gamma. It also produces a well-typed state. It produces an arbitrary type, and then an expression with some size bound of the appropriate type. Then it just checks whether evaluating in the state doesn't return a none. It doesn't fail. So let's test it and find our silly bug. Yes, there is a bug. Can you tell what the bug is or even where it is? Is it in conjunction? It could be in conjunction. We actually know it is. Is it have to do with equality? Variables? What is going on? And the moment you write your first generator and test your first property, you'll become painfully aware of how important shrinking is. Nobody, like every time I start a testing project, I think I can get away without it a bit, or I will be fine. And then you make an actual mistake that you're not just introducing to play with, and there is no way to figure out where the bug is. You have to narrow it down to where the actual problem is. So, how much time do I have? Oh, I have time. OK. The first thing that we could do is derive shrink for expressions and just plug everything in. So instead of calling for all and generating an arbitrary expression, we call for all shrink and provide the default shrinker with which to shrink the expressions that it produces. That could work. Well, here's the output. So if you call the expression soundness property with a conjunction of num and true, the property apparently fails. But that is not well typed. So why is the property failing? And the problem is that we don't actually have a check here that the generated expression is well typed. Well, our generator will never return anything well typed, but our shrinker does not preserve the well typedness. It does not know to keep only the correct, the well typed expressions. So the result is that we have a counterexample which could not be generated by a test. It does not